6.
All right. Get started with some good random questions. Break the ice. What makes acids corrosive, and what does the energy of corrosion look like? So corrosive can mean a lot of different things. One of the things that we see with acids is like the classic sci-fi idea from like going back to Alien from the 70s. You didn't realize the first Alien movie was released in the late 70s. Go check your timeline. Where like the acid spit from the alien like eats through the metal. So like the idea that an acid corrodes metal and eats through metal is pretty common, and that's mostly because when we talk about how reactive different elements are, basically metals can be more reactive than hydrogen gas. And what that looks like is if you put something that has that's a strong acid in water, what you really get is hydronium ions. Because if you put HCl as a gas in water, we're going to talk more about these today, so this isn't entirely a tangent. And I should be using the other reaction arrows right now. What you actually get is H3O plus and chloride. So this is one of the reasons why it's not aqueous, it's not classified as an acid, is because what an acid actually is it means when you dissolve something in water, you actually get more hydronium around. Hydronium doesn't really exist on its own, it only exists in a water-based solution as a result of having an acid present. So when you put an acid in water, you get lots of this, and what happens when you have lots of that and it gets exposed to a metal, like say aluminum, is basically you wind up turning the aluminum into a positive charge and making hydrogen gas out of it. So this isn't going to look balanced because there's some other things that go on with this. But basically you make aluminum, if you put hydrochloric acid on aluminum, you make aluminum chloride as a solution, and you make hydrogen gas. But what that looks like visually is that you're dissolving a metal.
Evaporates into a gas though?
So, and then what happens is because the product of this is making hydrogen gas, the hydrogen gas leaves. And so that's what if you ever put something in an acidic solution and it's like just a bubble, that bubbling is usually hydrogen gas. So, but that's not necessarily the whole story with acids, because the other thing that acids can do, acids are corrosive to biological tissues, mostly because the structure of most of our biological tissues is predominantly proteins. And proteins are just these big, long chains of amino acids that are all linked together in such a way and then folded in such a way that they have a specific shape. What happens when you change the amount of acid in the solution that has the protein in it is the protein actually winds up getting an extra H plus added to it. Just like we stuck an extra H plus on that water to make it hydronium. If you do that to some of the side chains in a protein, then all of a sudden you've changed the charge of the protein itself and it won't fold the same way anyway. So then it gets what we call denatured, which is basically means misfolded. And if it's misfolded, it can't serve the same purpose that it did before. So basically, most proteins, their function in the cell is highly dependent on being in the right pH. If you add extra acid or if you add extra base, either way is going to denature those proteins and they're going to misfold, which can cause tissue damage and looks like a burn. So that's actually what most chemical burns are. It's not actually from heat. It's basically from your proteins being denatured, which is the exact same thing that heat does to proteins as well. Heat denatured proteins by causing them to misfold as well. So that's why we still use the term burn and why it looks physiologically looks pretty similar. An acid chemical burn versus a heat burn looks really similar because it's the same end result. You've denatured your protein and then your immune system has to try and rebuild that and protect it and regrow those cells. Going along with that, with the biochem side, what are some things in food you should stay away from? I mean, anything that's known to be a carcinogen would be a good thing to stay away from. But for the most part, most foods that are commercially available in the United States aren't that bad for you. You know, there's long-term effects of eating unhealthy food, but unhealthy food doesn't necessarily mean dangerous food, especially if it's only done in moderation. It's like McDonald's, everybody knows that's not good for you. It's not the end of the world if you have McDonald's once a week. If you have McDonald's 2 meals a day for 10 years, you're gonna have some health effects. But if you have the same thing 2 meals a day for 10 years, it doesn't matter what it is. Basically, you're probably building up some nutritional deficits by doing that because we need to eat well-rounded diets for the most part. As far as things you can actually avoid that actually are harmful, it's anything burnt. Anything burnt, when you burn organic compounds, you make free radicals. Free radicals basically just means it's an organic compound, it's a carbon-based compound that has unpaired electrons in it. And unpaired electrons means that those molecules don't have complete valences, right? So they're super unstable. And so what happens when you have an unpaired electrons, when you have an odd number of electrons, is they go and they find an electron and they steal it from something else. But if it steals it from something else that had an even number of electrons, now we still have an odd number of electrons. So you cause this chain reaction in your cells when you ingest free radicals that basically can break down a whole bunch of different biological molecules that your body needs. And if it happens to hit the DNA molecule, then you can wind up with mutations to your genetic material as well, which is why free radicals are carcinogenic. Because most mutations to the genetic code are either what they call silent mutations, where nothing actually changes in the body, or they cause some form of cancer. 99% of the mutations, 99.9% of the mutations to your genetic code will just be a silent mutation where nothing happens. And then 0.1% cause cancer, and then 0.00001% have some other effect on your reproductive cycle or something like that. So for the most part, stay away from things that are burnt. And don't smoke anything. When you smoke things, you're doing the same thing. You're burning something and then you're inhaling it. So you're exposing your lungs to those free radicals. Even if the compound that you're burning, like THC is not inherently a carcinogen, but smoking weed will raise your rates of lung cancer, even though THC is not inherently harmful. So it's the route of administration in that case. When you burn things and then put it in your body, that's a problem. And that can even just be like you burn the steak on the grill. If it's black, it's not good for you to put in your body because it's got those free radicals. That also, don't take that as an endorsement of vaping over smoking, because vaping has its own list of health effects that we're still figuring out. Still not good for you. But that's more to do with the fact that you're putting tiny particles in your lungs of things that might be harmful. It's not necessarily free radicals at that point because it's lower temperature, but you are gumming up your lungs with these particles that can cause other issues. So I'm not going to tell you to not do drugs. You're all adults. You can make your own decisions, but it's not a good idea to smoke them and put them in your lungs. Or at the very least, you should know what you're getting yourself into. We've strayed from food, but it's similar in a lot of ways. The other thing, if you go abroad, make sure that you don't eat anything that has trans fats in it. That's one thing that we got rid of in the US in the last 15, 20 years maybe. Trans fats basically taste really good because a trans fat, a fatty acid chain is a big long chain of carbons with an acid group on the end that looks like this. A saturated fat will look like this. An unsaturated fat has a kink in the middle. So an unsaturated fat still is going to have the fatty acid chain over here, but then when it goes like this, you get a double bond in the middle. What that does is it bends this so it doesn't lay flat anymore. So saturated fats are solid at room temperature and they pack really, really tightly together because they're these long straight molecules. They can all pack like putting toothpicks into a toothpick, into a round cylinder. Right? You can pack a lot of toothpicks in there. If you could picture taking a couple of those toothpicks out and sort of breaking them in the middle so that they don't lay flat anymore, you can't put nearly as many toothpicks in that container anymore, right? So unsaturated fats are liquid at room temperature and they don't have as many calories in them, basically because per tablespoon, you can fit less molecules. And it also helps with keeping your cell membranes more fluid and less rigid, because you don't really want a whole bunch of saturated fats as the phospholipid bilayer in your cell membranes, because then your cell membranes aren't fluid enough. They start to get a little bit more rigid, like butter versus olive oil. And so you want lots of unsaturated fats, but what they figured out in the 80s is that if you make a trans unsaturated fat, a trans unsaturated fat looks like this. So you still put a double bond in the middle, but it doesn't add that kink to the fatty acid chain. So it has less energy to it, but it also is a solid at room temperature. It tastes a lot more like something like butter. So this was marketed as a lower calorie alternative to butter without sacrificing any of the taste of switching butter for olive oil or something like that. The problem is that these don't occur in nature, which isn't inherently a problem, but if something doesn't occur in nature, our bodies don't typically have enzymes capable of breaking it down. Our bodies are really good at taking fatty acids and breaking them down for energy when we exercise or when we're low on calories, but they don't have an enzyme capable of breaking down a trans fat. So they tasted really good, they had less calories, it seemed like a good idea at the time, and then they realized that if you eat trans fats, they basically become incorporated into your body and your body has no way of getting rid of them ever. They're then with you for life. Doesn't matter how much energy you need, your body can never use this for energy. It's like it's a dead end, basically, metabolically. So we've outlawed those. Most affluent, developed nations have outlawed trans fats. They're still pretty prevalent. They're really cheap and easy to make. It's easier to make a trans fat than it is to make a saturated fat in the lab. And it's way easier than getting this from a valuable crop like olives or some other source like fish oil or something like that. So they're still sold in parts of the world that don't have as much privilege as we do, that don't have as much money as we do, and that are less aware of the dangers of the trans fats. So you do still see them marketed worldwide. But they're definitely something you should avoid. A little primer on biochemistry today. Somebody asked me to recap why does water boil faster at our elevation. And it's not about rate, it's about temperature, right? So I'm going to go back to that phase diagram. Did I do that? Yeah. Yeah. I always have to think hard about which side gets the pressure and which side gets the temperature. That's normal. So if we draw our phase diagram for water, we have something that looks like this. If we look at, this is at 1 atmosphere of pressure, so at sea level. We have melting point at 0 Celsius, and we have boiling point at 100 Celsius. If we lower the pressure, we're shifting this dotted line down. This is an extreme case, really the differences we're looking at are not this pronounced, but if we're at 0.8 atmospheres, like we are at Tahoe, what happened all of a sudden is we shifted our pressure down, so now this cross section where we're looking at this is at a much lower temperature. We're seeing a boiling point happen at a much lower temperature because we shifted where we are on this phase diagram. And the other way of looking at it is that, I won't get into vapor pressure right now because it's beyond what we need for this class. But basically it's the result of the shape of the phase diagram. When you shift the pressure, you shift where this cross section is we're looking at. If you shift that cross section, you're going to change, in a lot of cases, both the freezing point and the melting point. It's just that with water, this is close to vertical, so we don't see the freezing point change as much as we see the boiling point change. The boiling point shifts by about 6 degrees for us. It's usually closer to 94 Celsius for us. And we can actually measure when we have a storm coming in. We'll see that shift. I've seen the boiling point up here as low as 91 degrees when we had a storm coming in. Because when we had a storm coming in, the barometric pressure is lower. And so you can actually tell when a storm is coming in if you just boil water and you watch the temperature where it boils, which is kind of fun. We've talked a little bit about energy content or about biochem. Somebody asked a question about energy content of fat versus protein versus carbs. Basically, it just has to do with how well your body breaks them down. Turns out that all of these carbon-carbon bonds, and the ones that aren't shown are carbon-hydrogen bonds. Carbon-carbon bonds and carbon-hydrogen bonds are not as stable as carbon-oxygen bonds. So what our body does when we ingest anything that it can digest is it takes these carbon-carbon bonds and it turns them into carbon-oxygen bonds, turns it into CO2. When you turn it into CO2, that's why we exhale CO2. And then what that looks like is our body has a bunch of different pathways in place that take that energy and turn it into NADH or FADH2, which then factors into the electron transport chain. If you take biochem, that you get a whole, do a whole unit on this. Take upper division biochem, I spent 8 weeks just on the Krebs cycle and the citric acid cycle and glycolysis in the electron transport chain. But basically, there's more carbon-carbon bonds and more carbon-hydrogen bonds in fat than there is in carbs or in proteins. So there's more energy content that your body can digest and produce. I want to say it's something like, I'm going from memory here. I think carbs and proteins are like 4 kcals per gram, roughly. And fats are something like 7 or 9 kcals per gram. They're almost twice as much energy in fats as there is in proteins and carbs. But fats taste really good. And that's by design. That's a evolved response. We really like the taste of fats because if you're in a hunter-gatherer society, fats are not something that you get very often. And you're probably running at a calorie deficit most of the time. So when you find fats, or evolution has trained us to gorge ourselves on things that don't show up very often, like sugars, fats, salt. Unfortunately or fortunately, we're now really good at producing those things really cheaply. And so basically, I don't know if hacked is the right word, but food manufacturers have gamed our predispositions to the point where all the things that are really, really good to us, that are really addictive to us to eat, are high in fat, high in sugar, high in salt. And that's why. Because it's something that our bodies need. I got a bunch of different questions. I can tell you all are getting worried about the final, because I think close to half the questions on the quiz this weekend were about the final and what it's going to look like and when we're going to start to review for it. which is reasonable. And it's gonna be even more important than you may have thought, because remember how a couple weeks ago I said if I kept seeing AI answers on the quizzes, I was gonna start shifting how much the quizzes were worth and how much the final was worth? I'm still seeing a lot of AI responses on the quizzes. So this is good news if you did poorly on the polyatomic ions quiz and the elements quiz, because that category will be worth a little bit less. I'm not gonna shift the assignments category very much because that's mostly just labs. You're doing those with me. So for the most part, I can leave that at 50%. I think basically what I'm gonna do is the quiz category is gonna be shifted down to 20% or maybe even 15%, and then the exam category is gonna be shifted up correspondingly. If you haven't been using AI, this is good for you because your quiz scores have not been as good as the people that are using AI. So your quiz category will be less important and the exam will be more important, and we're going to work on practicing for that. And get you really looking good, and feeling more confident about the test before we get there. So what the final will actually look like, and the way we're gonna review for the final, I'm gonna give you a final. I'm gonna give you last year's final. And nothing's gonna change when it comes to the structure of the final. Might be some, basically I'm gonna switch out what the reactions are, I'm gonna switch out what the numbers are, what the conversions are, but for the most part, it's gonna be the same test. It's gonna be 10 pages with a lot of white space because you have to show your work. Don't panic. And it'll feel like a book when I hand it out to you, because I'm also only gonna print it one-sided so that you have the back of every page for scratch paper if you want it. And so it'll look intimidating. Don't worry about it though. I don't usually have a problem with people finishing it in 2 hours. Usually the first person finishes the test about an hour in, most people finish about an hour and a half in, and there's always 3 or 4 people that will sit there as long as I let them. And so if I let you sit there for 4 hours, I would have people sit there for 4 hours. So I don't let you do that, but those 4 people, I'll cut you off at about 2 hours. Unless you have accommodations through SAS, in which case they'll have your test and you'll be taking it with them. But yeah, I'm going to give you, and I've talked to some people earlier this week that are nervous enough about this test, they want to see the practice test now. I don't usually do that, but if you all want to see the practice test now so you can start working on it, absolutely. By the end of the week, I'll have a practice test for you. And just right now, we can look at it right now. I'll show you what it looks like. Struggling.
It's very interesting.
This is from 2020. So the format will be a little bit different because this was COVID year. So I had to put in more stuff about don't use stuff on the internet, and AI wasn't a thing at the time, but the structure of it's pretty much the same. It's gonna be a couple of explanation questions, basically vocab, but I'm gonna try and structure the questions so that you can, it's less like, give me a definition for density and more like, explain how density does this or something like that. So I give you a little bit more direction. But this is question 1. It's gonna be 5 short answer questions. Explain some various concepts, explain what an orbital is, or explain, how a Lewis dot structure works or something like that. Explain the relationship between charge and atomic number. Like, well, atomic number is the number of protons, which is like, so basically short answer, 1-sentence answers for this part. These 5 questions are going to be worth a total of 10 points, so 2 points apiece. Question 2 is all about, can you do arithmetic on your calculator? Do you know what to do with the units? And do you know how to round for our sig fig rules? So 10 points is just, can you punch this into the calculator and know where to round? You know which units cancel out. I think most of us are pretty good at this point, and as, again. I'm not gonna be overly harsh on the sig figs, say, I'm trying to give you points here, so get close on the sig figs, do the best you can, don't worry about getting it perfect. You can get it perfect, but I should also say, this is not I'm not bragging about this, I've never had a student they got a perfect test. And that's fine. I don't think I could get a perfect score on my test in a timed situation, and I wrote it. Right, there's just too many places to mess up the rounding, there's too many places for sig figs to go wrong, or for me to be in a rush and mess up a Lewis-Dot structure or something like that. That's fine. The point of the test is not to get it perfect, the point is to get as many points as you can. Part 3 is nomenclature, including polyatomic ions. Did you ask about polyatomic ions? Yeah, polyatomic ions are going to be on here. So I assume you still know your polyatomic ions. They're not going to be an entire page on the polyatomic ions, but there's some of the points in here. So it's like, if I give you the name, you give me the formula. If I give you the formula, you give me the name. And again, this was more for the COVID year where they hadn't opened, it was open book. So I changed, the bottom part's changed. Just going to be name to formula, formula to name for this class. 10 points for counting protons, neutrons, and electrons, and doing an electron configuration. This is fast. This should be, I would love to give a 10 out of 10 to every single person in the class for this problem. I never do. It's easy enough to mess up electron configuration. I'm not going to put any of the ones that have exceptions on here. These ones are all going to be filled up in the order that we've practiced. I'm not going to ask you about anything in the middle of the D block, for instance. But if you can count protons, neutrons, and electrons, you can do electron configurations. Easy 8 out of 10. The way I'm going to grade these is this box is 5 points. 1 point, 1 point, 1 point, 2 points. If you get even halfway close on the electron configuration, I can give you half credit for it. So you should be able to get an easy 8 out of 10 on this page and quick. Page conversions. I'm going to make you do a long length conversion, like centimeters to miles. And I'm going to say that you have to use the equalities that I provide. You can't, if you have something memorized, I don't think anybody would do this, but if you had the conversion for centimeters to miles memorized, you're not allowed to use it. You have to use the ones that are on your conversion sheet. But that simplifies things. You don't need to worry about what to memorize because it's all on your conversion sheet. So there'll be a long length one. There'll be a temperature one, because that's a tricky sig fig question, because there's this addition and subtraction in there. If the practice test has you going Kelvin to Fahrenheit, it's a pretty decent chance that the test is going to have you going from Fahrenheit to Kelvin, right? Or maybe I'll just switch the number and leave it Kelvin to Fahrenheit. Either way, you know how to do that. There's going to be a volume question where you have to look at the cube. Like going from centimeters to inches, but cubed. Remember when we did that? Number 3 is going to be a volume conversion. And number 4 is going to be a combined unit, like a speed or a density. So, yeah, you're going to have to go back and review these things. But I'm telling you right now exactly what type of conversion I'm going to ask you about. The point is not for me to trick you or for you to have to guess what the test is on. The point is for you to practice these 10 skills, these 10 pages, because these are what I think are the most important skills. Everybody's favorite, Lewis-Dot structures in molecular geometry is a polarity. Same thing as the counting protons, neutrons, electrons. This row is 5 points. This row is 5 points. Probably 2 points, 2 points, 1 point. So draw me Lewis-Dot structure. Tell me what the molecular geometry is based on the Lewis-Dot structure. Tell me what is it polar or not based on the geometry. If you know it's there, you know how to review for it. I'll help you review for it. I'll give you the key to the practice test too. Not I know I keep saying this, and I know it seems like maybe I'm not trying to be discouraging or condescending or anything. All of the skills you can do. It's just getting there's just a lot of them. And it's just knowing what skills to be using in which place. And that's what we're practicing. This is also a place where I'll use that wrong but consistent approach. If you screw up your Lewis dot structure, but then you get the right molecular geometry for the Lewis dot structure that you drew, I'm not going to mark you down on your Lewis dot on your geometry. Because yeah, you messed this up, but at least you're consistent. You can be wrong, but have a consistent answer, and I won't mark you down. Let's write WBC. Wrong but consistent. And same for polarity. If you get this right and this right, but you mess up polarity, then I'm going to take away points. But if you get Lewis dot structure right, molecular geometry wrong, but then your polarity answer is consistent with what you wrote there, then I only have to mark off points once. Right, so more important to be consistent internally with your own answers than it is to get the right answer. I don't really care if you know if this is polar or not. I care if you know about the process. So show me you understand the process. Or at least part of it, so I can give you partial credit. And then we get to stoichiometry. 7, 8, and 9 are stoichiometry problems. So 30% of the test is stoichiometry. Balance this reaction. Tell me how much product you can make in terms of moles. The first one, 7, is going to be relatively simple because I'm going to give you moles and moles. You don't even have to do any atomic mass conversions. You just have to tell me how much product you can make. And then 8, still stoichiometry, looks really similar. It's a little bit more complicated because I give you a grams and then I ask you to give me atmospheres. We haven't talked about gases yet. That's what we're going to do next week. But once we talk about gases, that's just another way we can get from moles to atmospheres. So it's still just a stoichiometry problem. And then in week 11, we'll talk about concentration. So your last stoichiometry problem is I'm going to give you some concentrations and you have to tell me a final answer. It'll either be what's the final pH or it'll be what's the final concentration of something depending on timing and how far we get. Right, so if you thought that Monday's lecture seemed okay, I need to work on that. I'm not comfortable with it yet, but I understood what we were doing. Then you've got 30% of the test. And I know everybody in here can count protons, neutrons, and electrons by this point, even if you have to go back and review it. Everybody can do that. Everybody did really well on that quiz online. So at least ChatGPT can do it. But you'll get there because you won't have ChatGPT when we do this. And it's not that tricky if we know it's coming in advance. The one surprise is problem 10. Problem 10 is what I call the wild card question. Problem 10 just separates A's from B's on the test. You can get a B on this test and barely even touch the last page. If you want an A on the test, you're going to have to give me at least a plan for how to solve a word problem. Even if you get hung up on the specifics or you run out of time, if you can just give me the roadmap for what you were planning on doing, and I can give you partial, if you're just writing the roadmap, like I'm going to do this, convert this to this, and that's going to be my final answer, and just don't even put in any numbers whatsoever, I can give you 5 out of 10 on this one. What I typically see is when we get to the end of the quarter, you all are going to look at your grades and you're going to realize, hey, to keep my B, I only need a 40% on the test. And you're going to phone in the test. That's fine. The class is designed that way on purpose. I don't like that because it's a lot more fun for me to grade tests when everybody's doing great and trying hard. But if you left this page entirely blank, I'm trying to think, probably a third of my students last time I taught this class left this last page blank. And I still only had like 3 that showed up and took the final that didn't pass. So you can leave this, if the word problems and the conversions is really intimidating to you, don't stress about this one. Get your 90 points on parts 1 through 9, or get 80 points on parts 1 through 9. And you don't even have to think about this. If you've been putting in the work, doing the labs, doing the quizzes, showing up, you could almost not take the test and still get a C in this class. If you've got a 90% going into it, depending on how I reset these scores. So I'm not telling you this like you don't need to keep working. I'm telling you this that if you've been putting in the work, don't be intimidated by the test. You've got this, and the test can't hurt you. Right? Because if you've been putting in the work and you're sitting at a 95% in this class, you get a 50% on this test, you've still got to beat. Right? So the whole point of the test is for you to show me in a controlled environment where I know you're not using AI, that you can do these skills we've been practicing. That's it. Right? It's not to try and get you to cry and quit science forever. That's the last thing I want to have happen. You can do this. So don't panic about it now. Still got 3 weeks to prep for it too. Any questions? I will say about this wildcard question, I will give you the hint, especially those of you who are here today or that are actually going to watch the recording. Energy didn't show up anywhere else on the first 9 pages, right? But we've spent a significant amount of time on energy. This one's about energy. Odds are your wild card question, your word problem you're going to have to solve on the fly is going to have something to do with energy. And it won't be a super tricky mathematical algebra problem. It'll be something that if you can think on your feet and think in conversions, you should be able to do that. Something involving densities, maybe something involving, the amount of sunlight that hits the earth, or I'm not actually giving anything away there. That's just, I'm making something up off the top of my head. It'll be something related to energy though, probably. All right. And then the last 2 or 3 pages is just you're going to get a fresh equation sheet, fresh periodic table, including electronegativity values. So you won't get to use your personal periodic table that you've been taking notes on this whole time and coloring in. But if the first thing you did when I handed you a test was you went to the periodic table and you started coloring in things or writing notes back on it, that's fine. I don't mind that. You just have to have the specific notes you want to write on it memorized for 10 minutes while you wait for me to hand the test out. And then you can write it on there yourself. I'm just not going to let you take a whole page of notes for the test. All right. How do we feel about that? Most people don't enjoy tests. That's fine. You don't have to like it. We're going to get you good at it, and so that you at least feel confident going into it. I thought I didn't like tests until I'd not taken any tests. I was in grad school, and after your first 2 years of grad school, you don't really take classes anymore. You just work on your research. And when I left grad school and I started looking into teaching, I took some of the certification tests to be a high school teacher, to be a sub. Basically, they have you take these subject matter tests. And so I just went into it blind, and I took the physics, the chemistry, and the biology one all the same day. And I had no prep time whatsoever for it. I just sat down and I got this huge adrenaline rush. I realized maybe I like taking tests. It felt like going into a sporting event, like I was getting ready for a rugby game. But think of it that way. It's not anxiety. You're just amped. You're excited. You're ready. It's all in the attitude. All right. More relevant question. Now that we spent 45 minutes calming you all down about the test a little bit, let's talk more about energy. Somebody asked about, why is it not? There it goes. When we do delta T, we always subtract final temperature and initial temperature due to the to get temperature change. That is the definition of delta. Delta of anything means the final value minus the initial value. So delta, the change in time is going to be your final time minus your initial time. Your final weight is your initial weight versus, or your final weight minus your initial weight. Delta always means final minus initial. So if we're trying to find final temperature, we're just doing the algebra to solve for that piece. Right? If I ask you the final temperature and you know delta and you know the initial, we're just doing a little bit of algebra. Plug in the initial, plug in delta, solve for final. So yes, in this case, it does say when finding final temperature, we add specifically what you're adding. The way I answer like questions like this, so are we going to add or subtract? I don't know, write it out, do the algebra. You just have to look at and say, okay, if I'm solving for that, I need to add T initial to both sides. If I'm solving for T initial, then I have a negative sign I have to worry about, but it's still just solve for that value. Okay? Is it possible to mathematically prove energy is conserved whenever two objects at different temperatures touch? I mean, technically, no. We don't prove things in the sciences. We actually prove things wrong. We falsify things. All we can say, we don't 100% know that this is true, that energy is conserved. All we know is that for the last 1,000 years since the law of conservation of energy was discovered, I think that was probably Newton, if I had to guess. So 500 years, every time we do one of these experiments, we always see the energy coming out to be the same on the other side. And no matter how we try to break that, it always still winds up being true. So we never prove anything in the sciences. We just disprove things. And whatever's left, once you've disproven everything, is our best guess for how the universe works. If you want more reading on that, the modern scientific method was best written out by a guy named Karl Popper. He came up with the idea of we don't prove things. A good scientific theory should be falsifiable. Karl Popper is one of the most important and unknown philosophers of the 20th century. He's also the one who came up with the idea of the paradox of tolerance. You spend time online in areas that talk about social justice and tolerance versus intolerance. You've probably heard somebody talk about the paradox of tolerance. It's the same guy. Paradox of tolerance is basically in a tolerant society, the only thing that you must be intolerant of is intolerance. Basically, if you tolerate intolerant people, then the intolerant people will wind up in charge. And then you don't have a tolerant society anymore. And so Karl Popper was the first one who elaborated on that. And that's exactly what happened in Nazi Germany in the 30s. Is the people that were intolerant eventually wound up in charge because everybody else tolerated them. So that's neither here nor there. Happy to talk about that in history more with you later. How do we do these things in the first place? We had to pick something. So basically, when they were first coming up with these equations, Q equals mCp delta T, they just said, well, we're going to pick water and make that our standard. That's why 1 calorie is the amount of energy it takes to warm 1 gram of water at 1 degree Celsius, because they just picked that as the standard. And then eventually later on, they figured out what a joule was, or they defined a joule. But basically, this number here in those energy units, we had to start somewhere. And so it's not really, that 4.184 number is not inherently useful. It's just useful because that's what we picked for our definition of what a joule is. Last case, and these are all relevant, there's a reason that I'm still spending time on this, reviewing this, even though we're an hour into class, 45 minutes. Why does steam cause more severe burns than boiling water if they're both the same temperature? If boiling water is 100 degrees Celsius and steam is 100 degrees Celsius, steam will give you a worse burn. Because what happens when the steam hits your skin, it's not just something hot next to something cold. It's also a phase change. Because that steam, when it hits your skin, is going to condense. So you don't just get hot water on your skin, you also get all that energy from that delta H of vaporization, which I don't have that one memorized off the top of my head, but it's close to, was it 100 joules, 100 kilojoules per mole? Versus plus, then you also still have hot water on your skin. So steam is way more dangerous than water is because of the phase change. Just like ice at 0 Celsius is a lot colder than water at 0 Celsius. Not really colder in terms of temperature, it's colder in terms of how cold it feels. All right, and then a bunch of you also wanted to go over a couple of these questions. I will give you a mea culpa on, I didn't put that other one in there. I messed up the formatting. I'm gonna go back to just doing fill in the blank. Every time I try to use Canvas's numbers system, it lets us down. So it doesn't allow units and it doesn't allow scientific notation. I'm aware of that, sorry. I keep trusting Canvas and I shouldn't. And also I think I left in I said 2.000 pounds space grams. I meant pounds, I just forgot to erase the grams when I changed the question. So that one's it's kind of a gimme. I didn't mean to make it tricky like that. And then I messed up the answer on it too, right? Because it said give me the answer in joules, but then the answer that it gave you was kilojoules. So I was just all sorts out of whack on that one. Don't worry about that one. Let's do the simpler one that everybody wanted to ask about. Water absorbs 9.20 kilojoules of energy. The initial temperature is 22.5. What's the final temperature? So in this case, we know Q, we don't know delta T. If you wanted to do this all in one step, instead of solving for delta T, you could actually plug in T final minus T initial and solve for T final. So we rewrote it as mass CP T final minus T initial. Then you need to worry about order of operation. Depending on how strong you are on algebra, you might not want to do this. Your easier option is to solve for delta T and then solve for T final. That's a little bit simpler in terms of doing the algebra. If you're going on in the sciences and taking more math, and this looks like something you can solve, this is a little bit more elegant. You can do it all in one step then. But totally your personal preference. You should get the same answer either way. We know Q is 9.20 kilojoules. But we can't leave it as kilojoules, right? Because our specific heat is in joules, not kilojoules. So we just convert 9.20 kilojoules. 1 kilojoule is 1,000 joules. I will remind you with these metric prefixes, make sure that your conversion makes sense. I know I'm behind on grading some of the labs, but I was grading the that energy lab with the flame tests. Where we had to actually do some stuff with energy in kilojoules versus joules. And a quarter to a third of you mixed this conversion up. But you said 1,000 kilojoules is 1 joule, or you just flipped them and you didn't make the units cancel out. So be paying attention to that. We know that kilo is bigger than the regular unit. So there's 1,000 joules is 1 kilojoule, just like grams and kilograms, or just like meters and kilometers. And so we're gonna multiply by 1,000, so 9.20 times 10 to the 3 joules. So we know Q, we know mass, we know CP, we want delta T. Just barely put that in there. That was probably hard to read in the back. Apologies. I just plugged in the numbers that we have over here. So divide both sides by 75.25, divide both sides by 4.184. You got delta T is
129. Yeah, there's 22 things, right?
3 sig figs,
Oh,
4 sig figs, 4 sig figs. The 2 sig figs are the, we're gonna, when we do the subtraction, we'll pay attention to it, but sorry, 29.2 you said? So once we know delta T, 29.2 degrees Celsius equals T final minus 22.5 degrees Celsius. So T final winds up being in the 50. Is that 51.7? Carry a 1 somewhere.
no.
Add 22.5 to both sides. Both of these numbers have their uncertainty in the 10th place. So our final answer is going to keep its uncertainty in the 10th place. So we're good to go. How do we feel about these Q1s? We can do the algebra, they're okay. Do your algebra and watch your units. Those are the easy places to trip up. All right, before we take our break, let's do one more review question, then we'll get to the new stuff, which is really just elaborating on stoichiometry today. We'll get to the new stuff after break. We've got another combustion reaction. Another hydrocarbon plus oxygen turns into CO2 and water. All combustion reactions look the same. The only thing that really ever changes is that and what the balancing is. This one in particular is another common molecule. Anybody know what this one is? Anybody do any welding in here? What do you use with the torch? It's been a long time. the cutting torch that you used before they had readily available plasma torches to cut metal was an acetylene torch. This is acetylene. So when you're cutting metal with one of those, with a welding torch, you're burning acetylene and oxygen. You have two tanks. You adjust how much you have of both of them, just like a Bunsen burner. So acetylene and oxygen. Start by balancing. I've got two, let's look at carbons. We can do, if we have one acetylene, we can make two CO2s, right? And if we have one acetylene, we can make one water. But that's a problem. Why is that a problem? The oxygens over here are odd, but we can only add oxygens in an even number. So the fact that we have an odd number of oxygens here, but we have to end with an even number of oxygens. So we're just going to multiply everything by 2. The easiest way to make an odd number even is to just multiply everything by 2. So 2 acetylenes can make 4 CO2s and 2 waters. Which now means we've got a total of 10 oxygens on the right-hand side. And 4 times 2 is 8, plus another 2 is 10. So I need 5 O2 molecules. So now that it's balanced, we can do some stoichiometry. If we have 5 kilograms of acetylene, our final goal is to know how many grams of CO2 we can make from that. But our first step with any of these stoichiometry problems is take the amounts you're given and put them in moles. Because in order to do a conversion where we're converting between moles of acetylene to CO2, it has to be in moles because that's the way we balanced it. We balanced it based on 2 moles of acetylene makes 4 moles of CO2. So put it in moles. 5.00 kilograms. Our atomic masses on the periodic table are in what units? Grams per mole. So we got to get kilograms to grams first. 1 kilogram is 10 to the 3 grams. And then we can use the atomic weights, right? Because we know the formula of acetylene is C2H2. So we can say, okay, well, the mass of 1 mole of acetylene is going to be 2 carbons, grams per mole, plus 2 hydrogens, grams per mole. If you're watching your sig figs for atomic masses, because we're going to be adding these, for the most part, you're just going to be looking at keeping the decimals the same as your least certain number. Both of these numbers go to the thousandths place, so I get to keep my atomic mass to the thousandths place. So it's going to be 24.022 and plus another 2, so it'll be 26.0 what?
Okay.
Thank you. Kilograms cancels kilograms, grams cancels grams, we're in moles. Like 200? Just under? Or 20?
192.
192. I can estimate that if you're trying to figure out tricks for doing the mental arithmetic, 26 is close to 25. 4 times 25 is 100, right? So I can do, I know, and then this is gonna be 5,000, so 5,000 divided by 25, I can estimate that is gonna be close to 200. Because I know of that, I'm just calling that close to 26 to 25. If we have that many moles of C2H2, we're trying to find grams of CO2. First, we need moles of CO2. So we can say 192 moles of C2H2. And we just look at the coefficients. For every 2 moles of acetylene burned, that's 4 moles of CO2 made. So 384. And then we go back to our final question here. We want grams of CO2. Or in moles of CO2. So it's just another atomic mass conversion. I'm gonna blank this out so I have room to work to do the last bit. Any questions before I do that on how we got here? So 384 moles of CO2. Grams of CO2, I just need the atomic mass or the molecular mass of CO2. So that's going to be 12.011 grams per mole from the periodic table, plus 2 oxygens. Oxygen is 15.999 grams per mole. I think it's 44, right? 0.020. 021. So 384 moles CO2 for every 1 mole of CO2. So when I say 1 mole of CO2, it's 44.021 grams. I'm just expanding that unit, right? Turning it into a conversion factor. And moles will cancel out moles. Or in grams. I think this comes out to be something like 11,000. That one's not mental arithmetic. I think I just remember the answer to this question.
like 16,899.
16,000.
You keep 3 6.
And we're gonna keep 368. So 1.69 times 10 to the 4 grams. Right, we're not doing anything new with this, we're just putting a bunch of pieces together in a new way. When you get good at this, when you get practice at it, you don't even need to stop here at moles. You can go straight from mass of acetylene to moles of acetylene, moles of acetylene to moles of CO2, moles of CO2 back to grams of CO2, all in one conversion if you wanted to, if you had the room. I'm just not doing that now because the point right now is to break it down into steps that you all know and are familiar with. Like building Legos. Individual Lego is not that complicated of an object, right? But if you put 20 of them together, it starts looking like something else. This is just putting together a couple Legos. All right, let's take our break. Let's come back at 11:35. And we're gonna do some logic puzzles with this. Because so 5 oxygen molecules total of 10 oxygen atoms. With every oxygen molecule, it's an O2. It's giving to you, and this is. You were saying?
Sure, it's 6th grade, 12th grade.
So on this side, you've got 4 CO2s. Every CO2 molecule has 2 oxygens, right? So 4 of them means a total of 8.
What you said?
Right, because yeah,
And I just.
we'll get there. You don't need to want to. Yeah,
Last time I forgot to ask, which was the bell work?
you remember what it looked like?
It was like energy.
Was it dark?
Yeah.
So it was light.
That's what I thought with the results I
Yeah.
got, but I just wanted to make sure.
No, that's, yeah, you should check. So yeah, that one was light.
Okay, thank you.
No problem.
Schedule. You like. Yeah, I guess it's a little confusion. But it was pretty like it was, and yeah, and he's with. It's gonna come QR code in the front, on one side. And then the thing with my rotation was in October, he's responsible for the event. So by then we had like there, I believe. Oh, yeah, that's not true. You know, it's gonna be doing that training. Yeah. So you got them in the final. Oh. Part of this time. This is nutrition. I dropped that last one, was on the right. Just listen to it. So yeah, it's like easier than 3 hours. Because it was interesting, it was funny. Yeah.
Yes.
Yeah.
Alright, so I'm not going to do the last piece here, it's same logic for doing this last piece. You want how many grams of CO2 are required to burn all the acetylene? We're just changing this to be 2 moles of acetylene to 5 moles of oxygen. And then using the molecular weight of oxygen when we switch it out. So it's the same steps, just that 4 changes to a 5, and then the molecular weight's different because we're talking about O2 now, not CO2. And we're gonna get more practice anyway. So, a couple of vocab terms. When we're doing this stoichiometry, when we're talking about these different reactions, there's a couple of key factors that kind of get their own name. Basically, if we know we have limited amounts of both of our reactants, or if we had 3 reactants or 4 reactants, whatever, if we know we have amounts for them, they're not necessarily going to run out at the same time, right? This, going back to our cheeseburger analogy, this is running out of patties before you run out of bread. If they're not going to run out at the same time, then one of them is dictating your final amount of product, right? Whatever's going to run out first is actually going to be controlling everything else. So we call that the limiting reactant. The definition of limiting reactant is it's the reactant that runs out first. So here's the reactions that we've seen before. Iron reacting with oxygen, so iron rusting. If we have 2 moles of iron and 1 mole of oxygen, how do we know what's going to run out first? I'll give you a hint, it's not necessarily the one you have less of. It might be the one we have less of. But we don't know because they're not being used up at the same rate. Just like our pieces of bread versus hamburger patties, right? We're using 2 pieces of bread for every 1 hamburger patty. So we could have fewer hamburger patties, but still run out of bread first. So in this case, if we want to show our work to figure this out, we don't want to just guess, right? I mean, guessing is a 50-50 chance, but even if you got the right answer, I wouldn't give you many points for it if you just guessed, because I want to see why you think that's the case. So the way we do this, there's a couple ways we can show this. The easiest way is to say, okay, well, if all iron reacts to make a product, how many moles could I make? So 2 moles of Fe for every 4 moles of Fe. That's 2 moles product. So we're just going to get 1 mole of Fe2O3 of iron 3 oxide. Everybody with me? Then we're just going to do the exact same thing, but with the oxygen. So I didn't leave myself much room on this slide, so I'll do it at the top. If we have 1.0 moles of oxygen, and every 3 moles of oxygen makes 2 moles of Fe2O3, we get 0.67 moles of product. Missed you on Monday. So which of these numbers is right? Multiply everything by 100 and think in terms of hamburgers. I have enough oxygen to make 67 hamburgers, and I have enough iron to make 100 hamburgers. How many hamburgers can I make? 57. So that tells us that the oxygen is the limiting reactant, because that's what's running out first. And so this also tells us another thing about this reaction, what's called the theoretical yield. The theoretical yield is how much product you could make if everything went well. If everything goes perfectly, what's the maximum amount of product you could make? So our theoretical yield is going to be 0.67 moles of product. If everything goes just right, then that's the amount of product we can make. You can't make 1 mole of product, no matter how well we do the reaction, because we don't have enough ingredients. And we call it the theoretical yield instead of just calling it the yield, because there's no guarantees everything's going to go right. If we're making hamburgers on the grill, there's a possibility that I burn some hamburger patties, right? We can't use those. So even though we had the ingredients to make 67 hamburgers, we might only actually make 60 hamburgers. There's a lot of things that can go wrong in chemical reactions too. And there's other factors that when you get further into science, we talk more about, like equilibrium. But basically this theoretical yield is, okay, all of my reactant reacts and everything goes perfectly, how much product could I make? And it's going to be the lower of the two numbers here. I have enough iron to make 1 mole of product. I have enough oxygen to make 0.67 moles of product. Therefore, this is my theoretical yield. And oxygen is our limiting reactant. Let's add the last piece here. What's left over? Excess reactant is whatever isn't running out first. So we know this is the limiting reactant. We know that our theoretical yield 0.67 moles of Fe2O3. If oxygen's our limiting reactant, that means that we're going to have leftover iron. We didn't use it all because we ran out of oxygen first. If we want to know what the excess reactant is, we just do another little stoichiometry step. Because we can say, okay, if my limiting reactant gets all used up, how many moles of iron got used? And we're still just going to go back to their coefficients. For every 3 moles of O2 used, that's 4 moles of iron used. Makes sense, right? We just did the same math step. We're just talking about both of our reactants instead of talking about product now, right? So instead of talking about how much product we made, we're talking about how much reactant we used. Because it's on the left-hand side of the arrow. So when we do that math, we get 1.3 moles of iron used. So if we want to know how much is left, we just think about the logic. We started with 2 moles of iron. We used 1.3 moles. Another 6-7 answer was thwarted by sig figs. Sorry, that's not used, that's left. Alright, so do you see what I mean when I say that these are all just logic problems? Once you know that you're just doing conversions, it's all about, did I make it or did I use it? Do I have enough of something to make that much? And think of it like planning a barbecue. Do I have enough cheese to make 50 hamburgers? Do I have enough buns to make 50 hamburgers? Do I have enough patties to make 50 hamburgers? How much is left over? There's always something left over when you go to the store and you buy a bunch of hamburger buns, right? How much is left over? You actually can use these same, I don't think anybody would go to this, I don't think even I would go to this level to plan a barbecue, but you could write it all out like a reaction. Plan it all out, figure out how much excess you're gonna have left over if you wanted to know down to the bun how much was gonna be left. Sure, it's literally the same math and it's the same logic as making a bunch of food for people. It's just that when we call it iron and oxygen and iron 3 oxide instead of hamburgers, it looks intimidating. Don't let it intimidate you, it's the same thing. We already did that one. Let's say we do this reaction, this is the last piece for what we call a reaction study. The last piece is, what if we actually do this reaction and I didn't actually make my total possible number of hamburgers, I actually only made 50 hamburgers. What's the actual yield? I dropped the hamburger patty on the ground and the dog ate it. And some people took 2 hamburger patties because they wanted to make a double hamburger. So as a result, I didn't actually get my 0.67 mole. I actually got 0.5 moles. If we want to know the percent yield, percent is always the same equation, right? It's always the part divided by the total times 100. There's part. That's not as much as I could have made. The total is the amount I should have been able to make. So the 0.67. So percent yield. Actual over theoretical or expected is the other way of saying it. Actual over expected times 100. So for these numbers for this reaction, 0.50 moles over 0.67 moles times 100. I know that's an even fraction, but I can't figure it out in my head. Divided by, so 3 over 4, 0.75, 75%.
74.6, yeah.
So within sig figs. And so percent yield for anything is always done this way. If everything went perfectly, that's your expected value, or that's your theoretical value. And then you take what you actually get, divide by that theoretical. And this is something that shows up all the time too. If you're dosing medication, you don't always get, if you're filling syringes, there's always a little bit left at the bottom of the bottle that you can't get. You might have had a bottle big enough to make 150 doses, But at the end of the day, you only got 140 doses out of it. There's a percent yield there, right? 140 is the actual doses divided by the 150 you should have been able to get. And times it by 100 gives you a percent yield. Right, so lots of different fields use this. Use this idea, and it's always the same. So let's do a practice. This whole thing, a lot of times called a reaction study. I'm gonna give you a reaction. I'm gonna give you starting amounts and I'm gonna give you an actual yield. I want you to tell me what runs out first. How much do I have as leftovers? What's my theoretical yield and what's my percent yield? I'm gonna give you all 10 minutes to work together to try and answer this before I start working on it. It's hard for me to sit up here if it's too quiet. So talk to each other. Work through this. Then I'll start working through it with you. If you have questions, knowing where to get started, just call me over.
Y nunca le dieron
Tenemos dos de 18 puntos. Que nos va a dar un activo. En el examen soy estado breakdown, memory breakdown, you could write better than what no sé, este examen, ves que esa es la cosa. O yo. Ay, que divulga te lo uso, si no son. Puedes pero lo que redondear ya me das el hecho con todo. Yes. Ah,
No todo lo redondeado.
Now, one part of the problem that is because kilograms and for that. You will have to take the time, but it's not mass. Isn't that top number this? What is that? Oh, the atomic mass. Yes, this. We can take this atomic mass, so for example, always when carbon, so okay, carbon. It's a two.
Yeah.
But like, plug it into the folder, so it's really to get that. And look at this, and put it. Just around. Yeah. Well, very careful. But it's all important for you. And the locking is because of the. Hello, it's me. Vivid. Me speak the project. I was gonna like that. Sí. And now I let us come. There's one. Pero bien, ¿no? Ya me cansé de estar en China. Like, is it like, where you're supposed to pero tenemos que no sé, yo no lo entiendo. I can't get these words right. I didn't even know about it.
Bye.
Microbiology calculation.
One have an site.
Can I like? Can I get it?
Did I mix those numbers in? Okay, I thought I did. I thought this makes sense the other way, but. Second guess, let's see.
In scientific notation, you are going to point to.
No, scientific notation is at like 4:26 times.
All right. How'd that go?
What?
Did you go anywhere? Did it go? First things first, when you get a reaction, make sure it's balanced. Are we good here? Just because I asked it doesn't mean it's wrong. It looks good to me. You always just wanna double check that. But one titanium and 4 fluorines on the left, one titanium and 4 fluorines on the right. So we should be good. Just always wanna double check. We wanna be in that habit. What's the next thing we do? Put everything in moles. You can put the actual yield in moles if you want. Might as well while we're doing that, just we've got amounts, put them in moles, because then if we're dealing in moles, that makes everything work a lot more simply. Right, it's a lot easier to count hamburger patties than it is to deal with pounds of hamburger. Right? So 2.4 grams of titanium. Straight off the periodic table. Thank you. All right, 47.867. 867. Thank you. Can't get away from it, can I? So something really close to 0.05. Little bit over 0.05. How much?
0.05, right?
0.05. 3.4. We have to keep 2 sig figs. So
Yes. Wait.
do the same thing for our fluorine.
The grams is wrong, it's 76.
No, 76. Oh, it's 76, not 67. Thank you. Should still come out pretty close to the same number, right? Probably the same within sig figs. So fluorine is gonna be 37.996.
Oh, because of
So something pretty close to 0.05 again, right? 0.06 maybe? 0.04. Went the wrong way with it. And while we're at it, we might as well do our product. Zero, 2, 8, 4. Right, we just took the same pieces, so 37.996 times 2 is gonna be 75.992. Plus the titanium, so plus another 47.876.
Okay, I see it.
Yeah, myself there.
Sumo todo, so you got one of these equals.
So once we have these numbers. Keep your units with them, so you know we're working in moles now. So we actually, if you understand the logic of this and you can double a number in your head. We can actually just look at these numbers and tell what's gonna run out first. Right, because we're using the fluorine up twice as fast, right? In fact, we don't even need to double any numbers. We're using the fluorine up twice as fast and we have less of it. So we're definitely gonna run out of fluorine first. But in the interest of practicing our new skills, and since we have to get the theoretical yield anyway. Okay, pick the one you think is gonna run out first. And use that to find your theoretical yield. Or the other way we can do this is we can say, okay, I'm pretty sure fluorine's gonna run out first. How much titanium is it gonna use up? So if I say 0.042 moles of fluorine, and every 2 moles of fluorine used is 1 mole of titanium used. So this is the other way of showing your limiting, what is your limiting reactant? If I use up all of my fluorine, I'm gonna use up 0.021 moles of titanium. Do I have 0.021 moles of titanium? Do I have that much to use? Yeah, I've got 0.05. I've got more than double that amount. So if I'm gonna use up 0.021 moles of titanium, I know that the fluorine's running out first. Right, so that's just a different way of thinking about limiting reactant and how I can prove what's running out first. Especially since this question asks us to figure out the excess reactant anyway. If I guessed wrong, I would get a number that doesn't make sense. If I said, oh, I'm looking at this, it looks like titanium runs out first. And I did the same math. If I used up all my titanium, every 1 mole of titanium is 2 moles fluorine used. To use up all my titanium, I would have to use 1/10 of a mole, 0.106 moles of fluorine. Do I have that? No. In order to use up all my hamburger patties, I need 100 hamburger buns, and I only have 42. So this isn't what runs out first. If you get an answer that doesn't make sense, it probably means that you mixed up your limiting reactants. You guessed wrong. It's all just logistics. Do I have that much? What am I running out of? How much can I make? How much is left? That's all it is. I'm gonna erase this one because it's wrong. Sometimes it's worth showing things done the wrong way so that you can see why it looks wrong. My old wrestling coach always used to say, you're never useless, you can always be a bad example. He usually wasn't talking to me when he said that, but Alright, so we know how much titanium is used. We know how much titanium is used and we know how much we started with, we can answer that excess reactant piece, right? We have 0.053 moles of titanium. We're gonna use 0.021.
Yo creo. No es uno, pues.
So 0.032 moles of titanium left over. Or if you're feeling like a chemist today, you could say 0.032 moles of titanium excess. So we just answered the first two pieces here, right? We figured out what runs out first, we figured out how much of the excess reactant is left over. If we want to know our theoretical yield, we've already got everything in moles, that's pretty easy too, right? Because fluorine is the limiting reactant, we know that that's the number we're gonna use for everything. So 0.042 moles of fluorine. Every 2 moles of fluorine. 1 mole of titanium fluoride. Expected. Okay, there's our theoretical yield. So excess. Limiting reactant. And theoretical yield. Last step is just our percent yield. We've gotten this far, percent yield's walk in the park compared to what we've already done, right? We already have an actual amount in moles. We have our theoretical yield in moles. If we left our actual yield in grams, in order to do the theoretical yield calculation, we would just need, or in order to do the percent yield calculation, we would just need to make sure our theoretical was in grams as well. It doesn't, because we're talking about the same compound, it's gonna have the same molecular weight, we'll get the same percent yield if we do it in moles or if we do it in grams, so it doesn't really make a difference. That doesn't work if we're talking about two different compounds though, because they're gonna have different molecular weights. So percent yield is always actual over expected. So our actual is 0.0284. Divided by our expected, which is 0.021. Gonna be like 130 something, right? mess up the calculation, can we get 135% yield? I put it on the board, but that doesn't mean it's right, as we found out in last week's quiz. Yes and no. Well, yes, but actually no. We can measure more than 100% yield. We can never actually get 100% yield, more than 100% yield. Conservation of mass says we can't make mass that we don't have. We can't make atoms we don't have. However, when we actually do these reactions in lab, we can measure more than 100% yield sometimes if we screw something up. Like, what if we actually went to weigh our product and we actually weighed some of the leftover titanium with it? Or what if we did this in water and we filtered all the solid out of the water, but then we still had some water mixed in with our product when we went to weigh it at the end? There's actually a lot of logistics ways that you can measure more than 100% yield, even though you can never actually get more than 100% yield. And so don't be thrown off. If your numbers are close to the same ballpark, that doesn't necessarily mean you messed up your theoretical yield. Because there's a lot of other things in the real world that can happen to give you something more than 100% yield. If we did a better job letting our product dry before we weighed it, or if we did a better job filtering out the stuff that was left over, or leftover titanium, we could get this number to be more realistic. But I just showed you a slide and asked you a question about to do that on a piece of paper. So you can't actually do any of those things. You're just stuck with the numbers I gave you. So say, yeah, I got 135% yield. Trust that you do the math, that you're doing the math right in this case, as long as you're not off by a whole factor of 10. If you got 1,000% yield, then maybe you messed up your math somewhere. But, and then if you get more than 135% yield or more than 100% yield, you might want to double check that you didn't mix up actual and expected. But once you give yourself a 1 over and it's close to this to 100% in either direction, don't worry about it. Don't stress from there. Yeah.
I got all the same answers, which is kind of funny, but my titanium mole is different. So I calculated it at 47.876 grams per mole, so 5.0 times 10 to the -2.
So titanium wasn't our limiting reactant, right?
No, it wasn't.
So if you had 0.50 instead of 0.53, that's not going to affect most of our numbers because for the most part, we were worried about this 0.042 because that's our limiting reactant. So the only number that was probably off was your excess reactant number.
Yeah, it was, yeah, but yeah, I thought it was funny.
Yeah, so because we'll find out as we do more of this, that the limiting reactant winds up being the most significant piece of it usually. That's the one that we're going to base all of our calculations on because that's what you run out of first. That's logistically speaking, that's what controls everything. That's our bottleneck. All right, good job today. I'm going to give you another one just like that for your quiz this weekend. Go through the same steps. Don't feed it to ChatGPT. That'll give you an answer, but it's not going to help you on the final test. If you really wanted to, I don't recommend it, but you could check your answers with that. Do it yourself though, and show me a picture of your work. That's better. Actual intelligence is better than artificial. Yeah.
Me too. Absolutely.
It's sometimes the relation. So it's the reactive moles. And the reactive mold, shake those on bottom, your product. If we have a reaction, that's not what it's like on the offense. Then we're gonna have to, it's a, it's the same. Here's that one, it's. So like, in some cases.
Like, wait, so good. So they're like, oh, fingers, like. They're like, this month, you can.
If I have to keep products. I can figure out a theoretical yield for the silver, or I can figure out a theoretical yield for the zinc oxide. They're each gonna have their own theoretical yield, because this isn't balanced either, there's two there. And that now. But so they're not gonna be the same theoretical yield. Right, so usually what I would say is, tell me how many moles of silver, or what's your theoretical yield of zinc oxide?
So if we were to do this, let's say. Okay, the reaction. So we linear reaction times E. Two silver, 2 moles of silver over. One zinc.
Yeah, and let's just. Alright, so if we're doing we're doing this as variables, we use lowercase n for moles, so we can do moles of zinc. Times. Coefficient. Of the product. Divided by the coefficient. Of the thing. Will give you moles of silver.
Right, no.
It's, I don't usually write it like this because because it didn't really save us any space, and so as long as you're used to pulling the coefficients from the reaction.
Yeah, I just had to see it.
Yeah, sure.
These people.
Yeah, where's? Okay,
I'm guessing somebody emailed us and love this, because I'll just give you the.
yes, he told me he was gonna do that, so you won't get full credit, but you can get some points.
Try to put the data.
Yeah, just make a note of it. Yeah, thank you.
See you on Wednesday, since I hate you.
Okay, I'll see you on Wednesday, watch the recording. Okay. Let me stop the recording.